Okay, yay, we're recording. So welcome back. I feel like we haven't been together forever, other than the few that were able to pop into office hours yesterday. So yay, welcome back from our long hiatus. I ended up having some unexpected company over the weekend. You know, nobody's expecting company right now. And my parents showed up on my door on Friday. So very happy to have them, but it made it so I didn't record the lecture on regression, which we are fine because today we'll have ample time to go over chapters 10 and 11. So 10 is the regression chapter and 11 is the paired t-test samples. So I have been upgrading the notes on the regression chapter. Everything, you know, can always be better. So this version is not online yet because, I mean, it's like literally up to like 30 seconds ago upgraded. So most of the material is the same, exactly the same as the one that you'll get if you go to our class website. But this newer one will be up. I'll sync it after class today. But just FYI, if you're looking at it on your screen from online and it's different than this one that I'm sharing my screen on. So we'll go chapters 10 and we'll have plenty of time to go over the homework on 10 and then 11. The homework on 11, just as a warning in case you've tried it, 10 I don't have the Canvas assignment up yet, but there is the paper worksheet one. So let me get that. So can I open Sesame? Why are we not opening? Let's see. Too many things going on here. Okay. Don't go away. So many of these. There we go. All right. And then pull you guys back over to here. Okay. So on our class website, yeah, so 10, this link right here will, right now, if you open it, it is an older version, but we'll go over the newer version and then we'll do match t-test. The match t-test slideshow is very short. So in Canvas, the atomic assessment, or let's see if you go into yours. So chapter 10, for now, you can just go to the worksheet version here and work on filling it out here. And the link on the Canvas assignment works. There's just no place to put in your answers yet. The good news is now starting with chapter 11, the assignments exist in atomic assessment. So that's the good news. Yay, they are created. The holdup is when I created them originally last semester, it was my first time using atomic assessment and I didn't know how to do it the best way. I did not know how to add the margin of error for rounding on the answer boxes. So if you think you have the right answer and it's getting marked wrong, don't use up all your attempts. It might be a rounding issue. And I'm gonna go in and add the margin of errors, the plus or minus amounts on those values. Another thing is the negative values weren't always right. And here's a heads up. In chapter 11, section A, number 2B, the back of the book answer is wrong. And I'll add a little note in the Canvas assignment about that. But the back, so in 11A, number 2B, the back of the book answer is wrong. So we'll get those updated and I'll get your homework. And most importantly, I bet you guys are dying to know your exam's graded. So there's that. Other questions about things you want to go over or have questions about before we get into doing, you know, the lecture material, regression, and paired t-tests?
So I was wondering if, sorry, Laura, go ahead.
I was just going to ask, so assignment 10 will be up indefinitely, or?
No, we'll go over it now. As far as entering, let's look at the calendar, shall we? So our syllabus. So I'm going to look at this PDF version. Oh, it's opening it on my other screen. Okay, so we are supposed to have an exam that opens, oh my gosh, is this not insanity? Who else is feeling like this is insanity? We're supposed to have an exam today, tomorrow. How is that even possible? Oh my gosh, okay. I'm gonna percolate that as far as adjustments to the dates. How about that? So how about we do the regression chapter 10. We'll have a 10-minute break. When we come back from the 10-minute break, we'll address calendaring, and then we'll spend the rest of the time on the matched pairs t-test. Okay.
Sounds good.
So we have we will address it because it needs to be addressed, but I've got to digest that and figure out how we can do that without killing you guys, but still address everything, because holy cow, this is craziness. Okay, so I said we were going to do the new version. There we go. Regression. So Laura and Melissa, you both had comments. Was there a different comment?
No, mine was just on the calendaring, so you addressed.
Yeah, make them realistic deadlines. Yeah. Leah, Hillary, Kelly, Brian, Kimberly, anyone else? Okay. All right, on to regression. And so often it's said that in undergraduate, you're paying for information, and in graduate school, you're paying for opinions. And I think it's very true, because you guys are all fabulous students. You're very capable. You can read text. You can understand things. You've got a lot under your belt. We're dealing with more of the massagey, artsy, like in-depth, real world application stuff now. And regression, I'll tell you, is where it's at. This class that we're taking right now is called Statistical Foundations, and it focuses on ANOVA methods and t-test methods. And they are great methods, but they are probably not enough to get you through your own research, nor to read the journal articles that you're going to be reading that you'll need to understand in your career. Regression is probably where it's going to be for you in your own research and for your reading of literature. And the reason is regression is a lot more of a robust and more capable, I would say, methodology, and a lot of methodologies are based on regression. Mathematically, t-tests and ANOVAs are very, very simplified versions of regression, and regression can then be expanded. So regression is like the middle ground. You can simplify it down to ANOVA and simplify it more to a t-test, or you can expand it out more to a multi-level model and SCM models. But really, regression is the core, and that's why I really say you should never take this course and stop. This is a stepping stone to get you to regression. So the foundational ideas that we develop and flesh out and try to get stabilized in this class are a lot in a way to help you move into regression. So for this class, we're just going to touch on regression in its simplest form. So sometimes it's called simple linear regression. So we have one predictor and one outcome. And we're just kind of introducing it here, kind of as we're bridging the gap from independent t-test to match pair t-test, because we're covering the way you can go from independent groups t-test to match pairs t-test. The bridging idea is correlation. The lack of independence is correlation. And that's the idea in which regression is based on correlations and partial correlations. So we're just kind of waving to it on our way through. Really, if you are thinking regression is interesting, which I think is very interesting, hold on to the next class, because the next class will get so much deeper into regression. But we are just passing through. So simple linear regression. It's very important as a researcher to have a full toolbox. So we've got a z-test hammer, which we have found has very limited application in the real world. We have a t-test for independent groups hammer. And we have a version of it that, so we could say like a metric and a standard version for whether or not we do or don't have homogeny of variance when we have two samples. We're going to be filling your toolbox with more tools. So we want to make sure we have enough tools that you never want to see a nail, see a problem, and try to hit it with your hammer because it's the only tool you have. Everything looks like a nail if all you have is a hammer. So if all you know is ANOVA, you're going to try to use ANOVA to answer every research question. But often regression or some other method is going to address your research question better. So your data and your research question should drive which analysis you should be using, not the other way around. You shouldn't limit yourself to only answer questions based on what method you know. Which is why I love my job, because people come to me all the time and they say, I have this research question, I have this data, what analysis should I do? So we filled the toolbox. So here is the type of an example. And try to pick out the things that, flags that come up in here that might be similar to things that you see in your research domain. Dr. Ramsey conducts a non-experimental study. Who deals with non-experimental studies? Observational studies, yes. Education and social research and human subject is full of this. Non-experimental study to evaluate what she refers to as the strength injury hypothesis. It states that overall body strength in elderly women determines the number and severity of accidents that cause bodily injury. If the results support her hypothesis, she plans to then follow it up with an experiment to try a weight training program to see if that can help reduce injuries in older women. So first she's trying to look at the observational data and see is there any proof of concept before she moves into the realm of actually going to all the hassle of doing a real experimental study. Real, like it's a pain. So she has data from 100 women, maybe in an exit data set, who range in age from 60 to 70 years old. The women, so she found them somehow, but the women undergo a series of measurements that assess upper body and lower body strength, and the measures are summarized into an overall index of how strong their body is. Then over in the next 5 years, okay, so this is a pain too, because you got to follow people for 5 years. Observational research is not easy, but so she follows them for 5 years. The women's record each time they have an accident that results in bodily injury and describe the full extent of the injury. So there's a lot of qualitative research that could be done here, but we're going to focus on the quantitative numbers. So on the basis of the data, so we have this overall body strength index, and then she calculates an overall injury index for each woman. We're going to skim over the detail of that messy process. But so simple regression analysis is conducted to see if the overall index of body strength is a predictor of the overall injury index as the dependent variable. So the new languaging here where we have independent variable is the predictor, dependent variable depends on the predictor, that's our outcome. So the languaging that is used is very specific to the discipline you're studying. So mathematicians will often talk about these being predictors and outcomes, especially big data scientists and mathematicians, predictor and outcome. And I fall into using those terms very frequently, but a lot of researchers use the languaging independent variable, dependent variable more frequently, but they're interchangeable terms. Independent variables often abbreviated IV and dependent variable DV, and you'll see that on the slides and in sometimes even in journal articles I'll see that abbreviation used, but that's the terminology. So there's a couple different ways this researcher could go. So to look at the strength and direction of the relationship, she could run a correlation. So that's what we did in chapter 9. Correlation is a pairwise relationship. Order does not matter in correlation. We don't have a dependent and independent variable. We just have a pair of variables. And the parameter there is the correlation in the whole population. We use that rho, that almost P Greek letter. And if we're basing our numbers on just a sample, a subset of the whole population, we use the letter R to denote the correlation. So we did correlation last time we were together. This time we're going to talk about the same relationship, direction and strength, but instead of talking about it in correlation as a pair of variables, we're going to talk about it in terms of regression. Regression is different than correlation because we don't just have a pair of variables. It matters which one's the dependent variable and which one's the independent variable. Also, we talk about them in terms of Y and X. Y is the DV, the dependent variable outcome. X is the independent predictor variable. There, the statistic we use for the whole population, the parameter is beta. And if we're basing it on just the subset of the sample, we use a lowercase b. Now, lowercase b is APA specific for a regression estimated parameter. And that's very clear in the APA 7th edition, which was a little bit vague in the 6th edition, whether you use a beta, a capital B, or a lowercase b. It's a lowercase b to mean the regression coefficient estimate in the sample. Okay, so we've got correlation and regression. Now, when we are doing simple regression, where we only have two variables, one predictor and one outcome, correlation and regression can be used interchangeably. The strength of regression comes not in the simplest case, which we're looking at simple regression, but just so you know, the reason that regression is so useful is you can have multiple predictors of a single outcome. And so you can control for other factors. So often when we have an observational study or data, we don't have a random sample, and we can't, when we have a random sample, we can say that the two groups, if we have two groups, that they're equal in all ways except for whatever we did differently between the groups because we randomly put the people in the two groups. Observational, if we're looking at something like educational attainment, that's not something we can randomize. And people might be different to their like on this one, their body strength might have a connection to their injury index, their strength index, but there might be something else like general health. If someone is generally unhealthy, they're probably going to be less active and thus have a less strength in their body. Or there could be other confounding factors that would drive that relationship. So remember, we saw the plot that had the movies and the drowning deaths with Nicolas Cage movies, and we saw that they went up and down together, but it wasn't because there was a cause and effect between those two measurements. It was something else, a third factor, like the ice cream sales and the drownings. The third factor could be weather or temperature that is causing those two variables to look like they're connected. We can see an association, but it's not necessarily cause and effect because of a confounding factor, a third factor that is not measured or we haven't thought of. So the great thing about regression is you can control for or take into account these other third factors or fourth factors, these other confounding factors. So after controlling for age and education, after we parse those things out, is there still a relationship between body strength and injuries? So that's the great thing about regression, is we can do that. And we're not going to see that so much in this chapter because we're just passing through, just looking at the simplest case of regression. So let's see if we talked about all this. Why is the predictor the dependent variable? Some people call it a criterion. I don't hear that phrasing very much in your disciplines. A response variable, that's all the same thing. There is this languaging that you will see, it's a mathematical languaging. We say we want to regress y on x. If you hear that like languaging, regress blank on blank, the first variable, regress blank, that's your outcome. On blank, what comes second are the predictors. And that's something that you just have to memorize, the ordering that means. So if in the example that we looked at with this, that we started with the motivational example, we would want to regress injury index on body strength index, overall body strength index. So if we're going to predict y from x, that's the same thing as saying we're regressing y on x. The on x you can think of being from x or based on x. So it could be regressing y based on x. Kind of read between the words. Okay. So in correlation, order doesn't matter. We have a pair of variables. The correlation between variable 1 and 2 is the same thing as if you switch the order. Correlation, order doesn't matter. Regression, it does matter which one's X and which one's Y. You will get different results when X and Y are switched. So knowing based on a sentence which one's the predictor and which one's the outcome is very important. So when we run regression, we're trying to find the line of best fit for a predicting relationship, the line that best fits. So we already saw in correlation, we always plot our data first because Pearson's correlation coefficient, rho and R, only measure strength of linear, straight line, single straight line relationship. And regression is the same way. Now there are ways to make a quadratic relationship to have a bend in the regression, but we're not going there. We're keeping it simple. So way back in your algebra classes in high school, what's the equation of a line? Y equals mx plus b. You guys remember that? Y equals mx plus b. Did your high school teacher beat you over the head with that to memorize it? In statistics, we flipped that around, and it really, I came from a mathematical background, so my undergraduate was in mathematical education and chemistry. I had never took a statistics class until my first week in my master's program in statistics. You cannot get a degree in mathematics without taking a stats class anymore, but I was back in the dark ages and somehow I accomplished that. So this was really foreign to me the first time I learned regression, and I'm like, why in the heck did they flip the order? So when we look at the regression equation, it's y equals b plus bx. I was like, what in the heck are they doing? The first thing in the regression equation is the y-intercept. It's the b, y equals mx plus b. It's the b from your regular equation of a line from algebra class. We put a b with a little 0 because there's no predictor involved there. Then this second b, this b with the little 1 on it that's in front of the x, that's what we would have called M back in our high school mathematics algebra class. So the slope is now going to be called B1. And this is the slope for the first predictor. And the little zeros and the little ones are because in multiple regression, we have multiple predictors and we call them X1, X2, X3, X4. So the slopes are B1, B2, B3, B4. And then the one that doesn't have an X, the intercept is 0 because there's no X on it. It's just sitting alone. Sometimes this is called the constant term. Some software will label it as an intercept. Some software label it as a constant. I think R calls it an intercept and SPSS calls it a constant. I can't remember SAS. Anyway, doesn't matter. So there's another thing about this equation. Check out the Y. What do you notice about the Y? The capital Y. It's got this hat on it. Call this a hat. The stats language, hat, Y hat. Because if you estimate, you have to put a hat on it. If you estimate, you have to put a hat on it. This is not Y, the Y you observe. This is Y hat. It's the estimated Y based on the regression line. So I won't sing again today. So the regression works this way. The predicted Y for an individual, so this little I is for any individual 1, 2, 3, 4, you can index it, whatever person in your sample. So the predicted Y is equal to a constant intercept plus a slope times the X value for that individual. Xi is X is our predictor, the predicting variable, the independent variable for a given case or a given individual. Y hat, it's important that it has the hat on it. That's the predicted, not observed. It's based on the numbers, unobserved, predicted value of Y for a given case / individual. So the B naught, that's our Y-intercept, or it's called a constant. It's the predicted Y value when x is 0. Now, if we look at this red equation at the top, if you plug in 0 for x, what do you get when you take your slope b1 and times it by 0? What happens there? If you times something by 0, it becomes 0. So like, cross that out. What's left if you plug in 0 for x? All that would be left would be the intercept. So the intercept is your predicted y value when x is 0. A big round hole. I will sing again. I'm sorry. I'm not a good singer, Alex. Okay. Sometimes the betas, those B with the little 0, some textbooks and softwares will use A or alpha instead of beta. It's just a notation thing. Stats textbooks are fairly constant, but not totally. Sometimes you'll see it as an A. This B1 hanging out over here with the X, that's your slope of the regression line. And that is not the y-intercept, that's the slope rate of change. Does anyone remember from algebra class, slope is blank over blank? What is rise over run? It's the rate of change. How much we change y and over x. Change in y over change in x. Sometimes instead of putting the little 1 down there, they'll label it xy. Just a different notation if you're looking at a different book or something sometimes. Okay. Questions on the regression equation? Is something you guys have seen before? No, Laura, no? Okay, we're going to be very familiar with this for a moment. Okay, so I have to come back to this. This is a very, very big point. For correlation and regression both, always, 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 just because things go together, Nicolas Cage movies don't cause drowning. It's not a causal relationship necessarily. So regression does not prove causation unless you've randomized. If you've just observed variables co-occurring, it's a correlation, it's an association, but it's not necessarily proof of causation. We need to temper our language there. All the points don't fall exactly on the line. They're going to be close to it though. Okay. We're going to skip over here. So how accurate, some regressions are more accurate than others. Some predictions are more accurate than others. Some relationships are stronger, some measurements are noisier. So there's two main ways we try to attach a number to our accuracy from regression. And SEE, like C, but it's like an abbreviation, is standard error of the estimate. SEE. That's one. It's the standard deviation of our predicted y based on x. And there's two versions of the formula that are used a lot. This first one is the one we would use if we had to do this by hand on a paper. We take all of our y values. So for each one, we subtract the predicted value, square it to get rid of the negatives, add them all up, and divide by n-2. Sounds like degrees of freedom. And we square root it because this is a standard deviation-ish type number. The computer would do the sum of squared of the residuals and divide by the degrees of freedom. Gets the same number. Another option is the residual or residual error variance, MSE. This is usually abbreviated MSE. You'll see on a lot of computer programs that MSE outputted, and R is one of those. Let's see, how does that compare? This one, let's look at this. S squared YX, and this one is just plain SYX. What's the difference here for the MSE? There's no square root in the formula, so we put the square here. So if you have MSE, how do you get to SEE? Square root it. If you have the SEE, how do you get to mean squared error? Square it. They're just, that's the only difference between the two. Mean squared error is used more for statisticians. Standard error of the estimate is used probably more by researchers, but they're trying to capture the same thing. How accurate is our regression? In both cases, yeah.
Okay, so the first one, standard error, that's looking at like the standard deviation of our estimate, or the,
Yes. So it's it's like how close are our predictions to let's look at this picture. I'm a picture person. So here is a plot, a scatter plot, right? So each point is a person. We've got an X variable and a Y variable. And we've
Right.
drawn on the line of best fit, the regression line.
Mhm.
Are the points all on the line?
No.
No. They're scattered above and below the line. They're close to the line, but they're not all exactly on the line. So how close to the line are they?
That's the standard error.
Yeah, so see, these points up here are above the line. They're residual, or how far away from the regression line they are. Here, the positive ones are shown in blue. The ones below the line are negative. They're shown in green. So on average, how far away are they from the line, straight up and down? That's what we're trying to get at with these measurements. The standard error of the estimate is on average, how far above and below the line are the real observed values from the regression line predictions.
Okay, and then the variance, or
Is
the,
that squared?
is that squared? Okay.
Variance has a lot of great properties mathematically over standard error, but standard error is like, on average, how far away would they be? Would you expect? That makes more like application sense.
Okay, thank you.
Okay, so the degrees of freedom are n minus 2. What's n? N is the
Sample size.
sample size. How many people? Why is it minus 2? Because we're estimating a constant and the slope. We're estimating two things, and that's why it's minus 2. That's the simplest way you can put it. So when we draw on the regression line, we're trying to minimize the residuals, make the line that fits the data best. So these residual lines are as small as possible when we square them and add them up. That's called ordinary least squared regression. And that's the technique that was taught to you in your undergrad stats class. We tried to find the regression line because there's a lot of different lines you could draw around there, right? We want the one that best fits the data, and our criteria for best fitting is so that all the regression, the residuals, those lines straight up and down, if we were to add them, square them and add them all up, we'd get the smallest sum of the squared residuals. That's ordinary least squares methodology, or the technique to find the best regression line. It's not something you want to do by hand, but the computer's pretty good at it. Okay. So ordinary least squared says we want to figure out what beta naught and beta 1, the intercept and slope, what they should be in order to get the smallest total squared residuals. So here is a small data set. We got how many points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Really toy data set, 10 observations. We've got x-axis is our independent variable, y-axis is our dependent variable, 10 points. Is there a linear relationship going on here? Yeah, high on one goes with high on the other, low on one goes with low on the other. Is it perfect? No, but we've got 1 point per person. Now I've added some dashed lines. The vertical one, I put at the average value of x, and the horizontal one, the average of y. Where those two cross, we often call that the point of averages. The regression line, the line of best fit, will always go through the point of averages. Always, always, always. So the regression line, is always going to go through that point of averages. Its slope is dependent on the data, how correlated it is. So here I'm going to add in the regression line. So for this data, this is the line of best fit. The regression line is always going to go through that point of averages. Now I've added on here some green lines. This is how far each point is away from where? The green lines go from the points to the average of y. This is called the sum of squared total. It's how much total variation there is in the y values. Now I've changed and I've highlighted how far we're going from that mean of y, but instead of going to the data points, I'm going to the regression line. These are called, if we added up all those squared blue lines, the lengths, if I took out a ruler and measured all those blue lines and squared them and added them up, that would be the sum of squared explained. It's how much variance is explained by the regression line that's based on x. Okay, I'm going to change it one more. So here we have the total, how much each y observed value deviates from the average of the y's. Here's how much the regression line deviates from the average of y. And here's the last one. Here's how much the observed y's differ from the predicted y's on the regression line. This equation's very important. This is what all ANOVAs are based on, as well as regressions. It's the partitioning of the variance. Does everyone have the same y value in our sample? No. If they did, we wouldn't bother studying it because nothing would be going on. So when we have a measured variable that has variance, that people are different, we want to know, why are they different? Are they different because of this thing we hypothesize about or something else? So we want to know how much of the variance is explained by our predictor. How much variance in the outcome is explained by our predictor or explained by our model. So we can partition or divide up the sum of squared into a pile that's explained and a pile that's unexplained. When we say the sum of squared explained, that's explained based on the regression model or all the predictors in the regression model. And the unexplained is residual error. This is due to a measurement tool being not perfectly accurate or noisy. Does it depend on what the temperature is, the phase of the moon? If you're using, like if I'm taking someone's temperature, we know that some thermometers are more accurate and some are more noisy than others. If you're trying to measure someone's depression, there are some ways of measuring it that are more accurate and some ways that are more noisy. That would be the unexplained amount. Then there's also some things just are not that stable that have a lot of variance in them. Say like my anxiety level. What's my anxiety level? Well, it depends on a lot of different things. And if I measure it right now and 5 minutes later and an hour later and next week and next year, even if the underlying level is staying the same, the measurement might have some noise in it or some differences that show up. And that's all of that unexplained stuff goes in the unexplained or residual or sum of squared error pile. We lost someone on our call. Who fell out? I want to make sure. Oh, there comes Kelly. Okay. Get her back. Okay. Got you back, Kelly. Okay. So there are some ways that we use to summarize how well a regression model fits the data. And the most common one is R squared. R, does this sound familiar? Have we seen R before? Where have we seen R most recently? The letter R.
Pearson's?
Pearson's correlation coefficient. If we have one predictor in our model, the correlation of the predictor with the outcome, that Pearson correlation, if you square it, this is what you get. It's the same thing. They actually use the same letter to mean the same thing. It's very nice. So your Pearson's correlation between the one predictor and the one outcome, if you square that, it is the coefficient of determination. That's the phrase that they give to this amount. And it is the fraction of the variance, total variance in the outcome that's explained by our one predictor. Now, if we're, just as a side note, if you're doing multiple regression with multiple predictors, this is how much variance is explained by all of the predictors. It's like by the model overall. Here we're only, and there you've got, it's not just a simple Pearson's because you've got multiple things. You can't just add them all up, but just as a side note. I think that the textbook talks about, and there's a homework question that talks about the coefficient of determination, and it also talks about the coefficient of non-determination, which is something I had not seen till this textbook. It's just 1 minus r squared. So if we have, it has to, the total is 100%. So if r squared comes out to be 0.8, that means 80% of the variance in the outcome is explained by our model. Then how much is unexplained? If 80% is explained, then 20% is not explained. So if our coefficient of determination is 0.8, our coefficient of non-determination is 0.2, because there's only the two things: explained, unexplained, determined, non-determined. Okay. So the coefficient of determination for simple linear regression is Pearson's correlation between those two variables squared. So it's always, since Pearson's correlation is always between 0 and 1, positive or negative, when you square it, it's going to be positive, and it's going to still be between 0 and 1. So this is how we can language or convey how good or how accurate or how well our model explains the variance. So if the researcher we started out with at the beginning of class runs a regression model and the coefficient of determination comes out to be 0.8, then the researcher can say 80% of the variance in bodily injury can be attributed to whole body strength. The coefficient of determination is the proportion, or we can convert it to a percentage, of variance in the outcome. And the wordage we can use is accounted for, is attributable to, is predicted from, is explained by the predictor. So all of these phrases, accounted for, attributed to, predicted from, explained by, they all are ways of saying the same thing. We need an example to tie this all together. It's coming up. The other thing, this isn't as meaningful, none of this is, for simple linear regression because we only have 2 variables, but is more so when we have multiple variable. It's standardizing our coefficients. So there's a lot of languaging around regression that gets used interchangeably, and at the beginning it can be very confusing. So let's see. So I am using these terms interchangeably. Slope, the regression slope, the regression estimate, the beta value, the estimated beta, and beta weights. All of those things mean the same thing. So when we look at our regression equation, this B1, we can call that the regression line slope, and we can also call it the beta weight of whatever x is, the beta weight, B1. So we can, a lot of times we talk about beta by itself, but sometimes we standardize our betas. In APA, we show this not by just having the little b, but a little b with an asterisk subscript, superscript hovering up. The asterisk means it's a standardized beta weight. And that means that our x and our y variable have been converted to z-scores before we run our regression. This is nice because it talks about it, you can interpret the beta in terms of standard deviations instead of the units that it's in. I want to look at an example. Let's get into an example before we go through all those bullets. So I'm going to look at some data. Here's some data. Got a largest data set. So I've saved this as DF, the data set's DF. To get the scatter plot, I use geom point. To add the regression line, I use geom smooth, method equals LM. LM for linear model, and that draws our regression line in there. If we actually want to fit the model, so this just puts the line on the plot, which is nice, but if we want the numbers to know what the intercept and what the beta, what the B0 and the B1 are, we need to actually run the model. And the way you do that in R, the command is LM for linear model. So you take your data set, you pipe it into LM, linear model. The first thing in the parentheses is the formula. The formula is always the dependent variable, tilde wave, predictor / independent variable. Remember when we did correlation, where did we put the two variable names when we were doing correlation? When we did like the core dot test.
You did the tilde wave first.
We did the tilde wave first, and the two variable names came after. Because they are, correlation is looking how the two variables interact with each other. Sometimes we use a two-way arrow. With regression, one is predicting the other. So the dependent variable is on a different side of the tilde wave than the predictor. And then we have to say data equals dot because the formula comes first, not the data set. And the period after the data equals says the data, what is piped from above comes to this spot. Now, if you run just that much, and you might have done this on your homework, it will give you some very abbreviated output. To get the full regression output, you have to then also pipe on the word summary. And this will give you more output. It will give you what is like a traditional regression output from other programs. So, on R, this is what it looks like. So the first thing it tells you is the call. It's basically what you told it to do. It repeats what you told it to do. It adds it. Now this formula equals is optional. You can or cannot, you don't have to include it, but you can. Then it gives this information about the residuals, which I don't find super helpful, so I ignore. This is the real important part here, the coefficients. This first column says estimate. Think about this as like a matrix or a grid of numbers. The estimates, these are our beta weights, our intercepts and slopes. So always at the top will be intercept in parentheses in R. This is sometimes called constant in other programs, like I said. So this is telling us our little b with the 0, our b naught, our intercept, our constant value is estimated to be negative 0.0176. So if x value is 0, we're going to predict the y value is negative 0.0176. Then it will list the variable that you predicted y based on. We are predicting y based on x. So here is x's beta weight or x's slope. It's estimated to be 0.95964. It shows about 5-ish decimal places, but really in its memory, R keeps like 27 decimal places or some craziness. Okay, so that's important. It has standard errors next to it. And if you take the estimate and divide by the standard error, you get a t-value. These are called walled t-values. You might hear that sometime. It's basically trying to see if the estimate is different than a null hypothesis. And the null hypothesis is nothing going on. If nothing's going on, what does our regression line look like? It's going to be flat at 0. That's like the null hypothesis, that we have a flat line with a 0 intercept. Because 0 intercept, 0 slope would be a flat line right on the x-axis. Is this a flat line right on the x-axis? No, but we want to know, is it significantly different than a flat line on the x-axis? So there are the two parts. The y-intercept, is the y-intercept different from 0? And we get a probability that t, the absolute value is t, is greater than a value. This is basically the p-value. So this last column is giving you the p-value that goes with the beta intercept. So our intercept is estimated to be a value of 0.017. However, its p-value is not significant. So it's just we estimated our intercept to be this number, but it could be 0 because it's not significantly different than 0. The slope here, we estimate it's almost 1, 0.96-ish. And we look at its p-value. What do you notice about this p-value? Teeny tiny, right? We've got this e to the -6 and we got a less than, and then we get these stars out to the side, and we look down here, here's a little code. If we've got 3 stars, it's teeny tiny. So this is saying something's going on with the slope. The slope's not 0. There's evidence of the slope not being 0. Now, if we look down here, we've got at the bottom, we've got the residual standard error. We've got, it calls it multiple r-squared, but we only have one predictor. We don't have multiple predictors. So this is basically, this r-squared, that's our coefficient of determination. That, what number is it? 0.4999? It's almost 0.5. So about half of the variance in our outcome is accounted for or based on our predictor, is how you would read it. This adjusted r-squared is almost always, it's going to be very, very close to the r-squared. I wouldn't worry too much about it. It's more of an issue when you have lots of predictors. The adjusted r-squared is adjusted for bias. It's more accurate, but we're only going to do, you know, keep it simple. We're just going to go with the regular r-squared. And this F statistic, don't worry about it right now. The F statistic will have, when you only have one predictor, the F statistic will have the identical p-value to the T statistic.
Sarah, what did you call the multiple r-squared again?
Coefficient of determination, this one. R-squared is coefficient of determination.
And that's the variation that's predicted or expected from the regression line.
Explained based on it's the explained variance out of the total variance. It's the part of the variance in the outcome that's explained by our model. And we're only using one variable in our model to predict our outcome. One predictor. Yeah. Good points, all of you guys. Good comments. Okay, so this is junk data. It's made up data. We'll use an actual data set with actual variable names next, but this is just to show you that the pieces of the code and the pieces of the output. Now here I took the model and I piped on the word summary to get all of this stuff. You can also pipe on different things. You can pipe on conf int and you'll get confidence intervals around your estimates. So what was our intercept was estimated to be this negative teeny amount, but the confidence interval goes from a negative number to a positive number. So where does it intercept the y-axis? Well, it could be negative number, it could be positive number. We're not quite sure. But what about the slope? We got 0.77 to 1.15. We know it's a positive number and not including 0. It's more than 0. So we do have some slope to our line.
Hey, Sarah, the residual standard error, that's just that, trying to remember, from the regression line, that's...
Residual standard error, that's just that. Check it out.
Siri is talking about residual standard error.
Oh,
This one.
is that my phone? Huh, weird. Yep.
Residual, the residual standard error is the standard error, the residual standard error. Yeah, I think it's this one. See, this is the hard thing about regression is the math is the same, but everyone attaches different words to the math. Isn't that fun?
So that's talking about just the bit between
How far above and
regression
below?
line and how far it varies. The average of all those is
Yeah.
your residual error.
Yeah,
Okay.
Yeah.
Sorry, I was getting them all confused.
yeah. So this residual standard error is the same thing as the SEE, the standard error of the estimate, I believe. And see, 98 degrees of freedom. What does 98 degrees of freedom tell our sample size was?
100.
100, because sample size minus 2 is our degrees of freedom. Okay, so you can also ask for pipe. So we saw piping on the word summary gives you all this stuff. You can ask for just the confidence intervals. You can ask for just the coefficients. So the estimates are also called coefficients, are also called beta weights. It's the same thing. So you can ask, if you just type on the word co-e for coefficients, it'll give you, that's just the beta 0 and, or the B0 and the B1 that are right here in the output. It's just another way to just ask for just a piece of it. You can also ask for the predictions. So there's 100 of these numbers listed out here. This is the predicted outcome. So these are the Y hats. You can ask for the Y hats. You're not, on the homework tab, you do it a little differently, but you can ask for the predictions. So the last thing we need to go over before we can do a real example is the assumptions. So the assumptions, all models are wrong, but some models are useful. How useful they are depends on how well you meet the assumptions. So the first assumption is you have a simple random sample. Simple, meaning and random, at least we want to ensure two things: that they are independent of each other and that they're representative of your population. You cannot test this, you can just plan as best you can. The key here is we have independent observations. So you don't want to go get your sample that is, you don't want to like collect, you say, I want to study second graders. I've got 4 friends that teach second grade. I'll get their classes. Well, then you really have 4 clusters. The students in this class are more similar to each other than students in different classes. That would be a lack of independent sample. That would be a dependent or clustered sample, not a random sample. So we want independent observations. Second assumption is that a straight line best fits the data. There is no p-value test for this. The only way you can test this is to make a scatter plot with the g-on point or the g-on count and look at it and say, does this look like a straight line or does this look like something that's not a straight line? So plot your data with a scatter plot to see if a straight line best fits your data. This third assumption, and I threw up the fourth one at the same time, this third assumption is the one that causes the most confusion with people that come into my office for consultation, students and faculty alike. And it's this word that I have put in bold and capital letters that is the thing that catches people unaware. So the condition for linear regression is that you have a linear relationship, but that your Y variable is conditionally normally distributed. And people drop that word conditionally. And they remember from whenever they took a stat class, my Y values need to be normally distributed. But that is not the case. This does not mean that the Y values, if you plot them in a histogram, your Y values will make a normal curve. It does not mean that all your Y values together make a normal curve. It means that, I'm going to show this up here, this picture, that your Y values are normally distributed around your regression line. So if this was my scatter plot, now it's a really simplified one. See how all my points are above and below the line? About the same amount. So it's like we have this mountain range along the regression line where they're all normal curves along the regression line. So we'd have like this lining up a bunch of normal curves along the regression line. There's 2 things about this. 1, the shape is that it's normally distributed, and 2, that the spread outness of those normal curves are the same. This is the homoscedastic, heteroscedastic idea, like the homogeny of variance thing that we had with our t-test. With the t-test, we said the 2 groups had to have the same spread. Here, x is can be a continuous variable. It can be a categorical variable. Your x value can be any kind of x variable. Your Y variable has to be interval ratio continuous, and it has to have about the same amount of spread above and below the line, all the way from left to right across the line. That's what we mean by conditionally normally distributed with constant variance. The normally distributed and the homogeny of variance apply to the points being scattered above and below the regression line, not just by themselves. The only way to really check this is with what we call residual diagnostics. So every time you fit a regression model, you should look at the residuals to see if they're normally distributed and have constant variance, to see if you meet this assumption. Let's look at some, okay. And the way you do that, okay, so here's some generic code. The way you do that is after you fit a linear model, R is really nice. It knows you want to do this. You want to check your residual diagnostics. So after you fit a linear model, if you pipe on plot, it will give you 4 plots. So you can tell it which one you want. The most common one we want is this second one that R makes. So if you pipe on plot, which plot do we want to make? 2, the second one, it will give you, what kind of plot is this? QQ plot. What does a QQ plot try to show us? Normal distribution. And it does it of the standardized residuals, the residual values. Now looking at this one, how does this look? Are those residuals normally distributed? If they were normally distributed, the points would be
on that straight line.
on that straight diagonal line. They even put a dotted line there for you to see in this one. Isn't that nice of them? Now, are they perfectly on the line? No, but we don't see a big swing or a big S curve. They're mostly about on that line. So this one looks good for our residual diagnostics. You can also ask for a histogram of the residuals. And this is, these are base R plots. They're ugly as sin, and I would never publish them. But residual diagnostics don't get published. They're something you do in the privacy of your own home when you're fitting your models. They're not for the public to view. So it's okay that they're ugly. With the histogram, what are we looking for? We want to see what shape. That bell, nice bell curve. How does it look? Yeah, pretty good. The QQ plot looked pretty good. The histogram looked pretty good. They're showing us the same thing. Do we meet the assumption of normal residuals? And that's this Y being conditionally normally distributed. Y values for a given X value are normally distributed. Okay, so let's do an application, shall we? All right, so this is all old hat here. Packages, tidyverse to get all our pipe and our dplyr package and ggplot, Haven to read in an SPSS data set, furniture to make tables, Cs and stuff like that. I don't even think we do, but just in case. So I'm reading in the cancer data set, which is an SPSS data set. I'm renaming all my variables to lowercase, ID, making that variable a factor, treatment. Remember, there were 2 groups here, the placebo group and the aloe juice group, for the oral condition of the throat cancer patients at different stages of cancer.
Hey, Sarah, why did you change the name? I'm trying to remember, right? In the factor ID.
Right here, I didn't change the name. I wanted to make the ID variable instead of the computer thinking that the ID is 1, 2, 3, 4, 5. It's like their person number, their identification number. I wanted R to know it was a code, not a interval ratio number to do the average of it. So I said ID is equal to a factor version of ID. Why didn't I change the name? Because I was lazy. So I could make this factor with a capital F at the end, but I was lazy. In general, this is a bad idea to change something and save it as the same name. The only time I would do that if you're just changing it to a factor without adding labels to it. This one, I actually didn't change the name of the TRT variable. I made it a factor version and attached labels, and I didn't change the name. it's a toy data set. I think we're okay here, but it would be better if you like change this name to TRT and put an F or something else at the end so you know it's the factor version of that variable. Is that what you were referring to, Melissa?
Yes, but I guess I'm trying to figure out this step does what exactly?
Which, all this step,
The mutate, the two mutate,
these
that
two mutates,
my independent of my dependent, or what does that give me?
this is just like wrangling the data set in general. We haven't, let's decide what we're going to do. Okay, so I'm going to fit a regression model and look at their oral condition and see if age predicts their oral condition at intake. So how their mouth is doing, does that have anything to do with their age? I might have, now this is like toy data set, so you don't know anything about it, you know, we're making this up. But I might have a research question that says, do older people have more mouth sores? Or do younger people have more mouth sores? And I want to know, does age, is it related to or predictive of the oral condition before we even do anything, just at onset? So this total CIN is their total oral condition at intake. So when the study just starts, is there any connection with age and this oral condition? So I'm going to run a linear model. Now, which variable is the dependent variable here? The DV.
Total oral condition.
Total oral condition, which is the IV, the predictor. Age is doing the predicting of the total oral condition. So we could say oral condition at intake was regressed on age. It's one way to language that. And then I'm piping on summary so I get all this output. So let's see, it just tells us the model we fit. Yeah, we knew that. I'm going to ignore this residual thing because I don't know. It's supposed to help you know if it's normally distributed. Are the min and max about the same? Are the interquartile ranges? I find it really hard to judge that based on a 5-number summary. So I go right down here. So I'm going to look at my coefficients. So this first number, 4.7. This is the predicted oral, this is the intercept. The intercept is the Y value. Which variables are Y? That's our oral condition. So this is the predicted oral condition when age is equal to 0. What do you guys think about an age of 0? Laura, you're smiling.
Like, that's not possible to measure.
Gold star for Laura today. I know it's been a while since we looked at it, and we haven't spent a lot of time with this data set, but do you guys remember the age of the participants at all in this study? I'll give you a hint. They're like 30 to 70. No one in this study was age 0. What is it called when we make a prediction outside of the range where the data is observed? We observe people from age 30 to 70-ish, and we're making a prediction for someone age 0. What's that called?
It wouldn't be considered an outlier if it's the...
It's not an actual value, but we're making a prediction outside of the range of our originally observed data. It's called extrapolation. So it's really common in weather and global warming. So we have the temperatures measured here, and we're making a prediction for 2050 as way outside of the range where our data was observed. The intercept is often an extrapolation and therefore does not have a lot of meaningful value. The slope, however, does usually have very much meaningful value. So here, our slope here is 0.03. The way you interpret this is for every 1 year older a person is, we would predict their oral condition goes up 0.03. Now, the way I just said it has a cause and effect connotation. I should say, if a person is 1 year older than another person, we would expect the older person, who's 1 year older, to have an oral condition that's higher by 0.03. or for all people that are 1 year older than all other people, that 1 year difference in age is associated with a 0.03 difference in the oral condition. It's always for 1 unit of the predictor. Now this age was measured in years, so we say for each 1 year older, so additional year, the oral condition is 0.03 higher. That's the B sub 1, or the beta weight, or the slope, or the regression coefficient for the variable age. But if we look on that age line, whoa, did you guys get, did yours do that? I blocked it out, okay. If we look all the way at the end of the line, what do you notice about the p-value for the age predictor? It's not significant. The p-value is 0.21. No stars for you, age. Not significant. So it's saying the slope is rise 0.03 for a run of 1, but it could be 0. We can't rule out the fact that it could be 0. Also look at our R squared, our coefficient of determination. 0.06 or 0.07 if you round it up. So only 7% of the variation in total oral condition at intake is accounted for by the age variable. The age variable does not account for very much variation. 0.06 is a small amount. Plus, the age variable's slope is insignificant. So this regression tells us age is not correlated or not predictive of oral condition at intake, or there is no evidence that it is correlated. Now, on this one, let's see what's going on here. This time I'm taking here I took my data set and I went right into my linear model. These variables are in terms of the oral condition variable. I can't remember its units. It's on some wonky scale that they came up with, some index. Age is on years. If instead I do a step in between my data set and running my model, what am I doing in this mutate step? What am I doing here? Let's look at it. So what does mutate do? Creates a new variable. This first variable I'm calling, oh, that looks the same as before, but it has this letter Z on the end. Total oral condition to intake with the Z, that's equaling, and then over here, we have the command scale. The command scale, we saw this once upon a time. It creates a Z score, it standardizes. So what I've done, this step here, is it makes a Z-score version of the total oral condition and a Z-score version of the age variable. And I'm using those Z-score or standardized variables in my linear regression. When you standardize them, we get much the same output. We get an intercept and a standardized age beta weights. Now these numbers will be different. The p-values, let's see, check out these p-values. Let's look at this one specifically, 0.217. Let's look at what it is before we standardize. The unstandardized p-value. What's the unstandardized p-value? The regular variables p-value, 0.217-ish. When we standardize it, the p-value does not change. It's just showing less decimal places here. But the estimate changes because now it is in standard deviation language. So this, on this output, we would say for 1 year older, 1 year additional year in age is associated with an increase of 0.03 total oral condition units, whatever they may be. When we standardize it, we can talk in terms of standard deviations. So we would say for 1 standard deviation older, the oral condition goes, oh, we got this e to the -1. What does this e to the -1 mean? point, we got to move the decimal place one place. So it's 0.25. 0.25 is about a quarter. So I'm going to talk about that. So for one standard deviation older is associated with a quarter standard deviation higher on oral condition. Our units are now both for the predictor and the outcome are both in terms of standard deviations instead of whatever units they were originally measured in. The p-value stays the same. This is more meaningful if your units don't have any meaning. So if we're talking dollars or years, those units have meaning. But if we're looking at like the, I don't know, the Utah State Depression Scale, those units, who knows what they mean. So it might be more meaningful to talk in terms of standard deviations instead of wonky units. What about the R-squared? Did it change when we standardized our variables? Let's see. Here's the unstandardized. What's the R-squared? About 6.5%, our coefficient of determination. When we standardize our variables, what is it? About the same. Okay. All right. So correlation and standardization. So here, what is this code chunk doing? Core.test, that's computing by default Pearson's correlation coefficient. Notice where are the two variable names in compared to the tilde wave. Both of the variable names come after the tilde wave when we're doing correlation because they're just partner variables. Order doesn't matter. When we do regression, LM, where do our variable names go? One's before the tilde, one's after, because it does matter which one's the dependent variable, which one's the independent variable. So here's the outputs. Here's Pearson's correlation. What's the Pearson's correlation? 0.256. Notice what we get for the standardized beta weight. 0.256. The standardized beta weights are Pearson correlation coefficients. That's just a nice connection. Okay. I bet you have lots of questions. Let's take at least 10 minutes to do questions before we break, and then we'll come back with the calendaring and then the paired t-test. So homework questions or any questions about what we've covered here.
I have a homework question.
Okay.
It's in the R part of the assignment.
Do you want to share your screen?
Sure. Hold
Okay,
on a
let me
second here.
stop my screen share. Okay.
Hold on. Okay. All right. So I'm on this. It's about line 153-ish.
Okay, here I've got, it went on my other screen. Let me see if I can move it. Come on, how do I move this? Oh, right there.
Okay, so I just got stuck with trying to pass the regression equation into the new shoe pred.
Yeah,
Variable.
the shoe prediction one is a good one.
Yeah, so anyway, just a little bit of guidance there would be awesome.
Okay. Yeah, so I'm not seeing your screen anymore. Oh, there it is. Okay, okay. I'm having issues with my computer. It's not you, it's me. Okay. All right. The shoe prediction. Okay, chapter 11.
This is in chapter 10, right?
Yes.
Chapter 10, thank you. I'm looking at 11. I wasn't going to find it. Okay. Let's go up before this so we can make sure everyone's on the same page here, because we need the numbers from this output as well.
Okay.
Okay.
see. I
So-
think it's this one right here.
So we have three variables here. We have reading level, age, and shoe size.
Right.
And so this first one is is this the first one? The
I
first
think it's the first one.
regression is shoe size based on age. Yep.
Yeah.
So we need to write down these numbers on a piece of paper because we're going to need them. So if you have a little paper to jot this down, that would be great. I'm going to grab a pen. So this first one is shoe size being regressed on age. We have a beta naught or a B naught and a B1. We've got an intercept and a slope. For this regression of shoe size on age, the intercept number is estimated to be
The 2.95.
2.95. Yep, that's our estimate for our intercept. The slope or the beta weight for age is estimated to be
That's the 0.425.
0.425. Yep. Okay, so we got that jotted down.
Okay.
Now let's go on to let's see, what's the coefficient of determination, the R-squared value for that? It's 0.6.
Yeah.
And if you look at the age, where you have age estimate, if you go across the line to the p-value, it's statistically significant, right?
Right.
Age is predictive of shoe size. And we would estimate this for each 1 year older, that's associated with increase in shoe size of 0.425. And we could also interpret the intercept to be the shoe size for a 0-year-old is estimated to be 2.95. Now that's a extrapolation because none of the kids in our sample were age 0, but that's what it would mean. Okay, so now let's regress reading level on age. So the intercept is estimated to be a constant value of negative 2. Let's keep 4 decimal places at least.
2.7488.
88. And our slope or our age parameter estimate is
It's a 0.7631. Yeah.
if we take 4 decimal places,
Yeah.
0.7631. I want to note that we're only taking 4 decimal places. There are more, but we're only going to go with 4 because that's usually going to be close enough. And what's the R-squared value there?
That one is 0.9223 or just 0.92. Is that we're just doing 2 on that one?
92% of the variance in reading level is accounted for by age. That's a huge amount. That's almost all. Almost all of the difference in reading level can be attributed to differences in age. Huge. So age is very predictive of reading level. Statistically significant and effect size. R-squared can be seen as an effect size measure because it's a correlation, and then the p-value for the age estimate, it's like less than 0.001, it's 0.00015, is highly statistically significant. Okay, so now we're on to this next one. So my guess is that it's how we set this up. So you start, we're going to call it child new, starting with the child variable, bars, data set, dplyr mutate, shoe pred. Okay, so it's what comes after pred. So that is what you need to delete right now.
Yep.
Okay, so it goes down to how will we write the equation. Now I'm gonna, I can't type on there. So if we were gonna do shoe size, okay, can you guys see that? Let's see. Oh, there we go. You guys see that? Is that even legible at all? So now instead of putting X and Y, let me take my marker. That'll make it easier to see. We are predicting shoe size from age. Let's see. This is where I want my whiteboard. So we're predicting shoe size. So I put shoe with a hat on it. And it's going to be equal to some intercept plus slope times age. That's the format of a regression of any line, but the regression line in particular. The predicted shoe size it would be equal to an intercept plus a beta estimate times age. So you've already typed shoe pred. Now you're going to type equal sign and you're going to plug in the numbers. Yes, exactly. And then type out the word for that variable age. Beautiful. That's what you do. You use those numbers. Now, you put parentheses around the 0.25 times age. You can do that, but they're not required. Just if anyone was concerned about that. So that's how you predict shoe size based on our regression line. Now you're going to do another pipe and we're going to do another dplyr mutate. We're going to have 4 dplyr mutate statements. Now the second one we're going to do is for shoe resid instead of predicted value, the residual. Now what's the residual? The residual is the difference between what we actually observed and what the regression line would have predicted. So the actual shoe size we measured was the variable named shoe. S-H-O-E.
Did I do something wrong there?
Just type shoe.
Oh, shoe. Sorry. I'm sorry. Yeah.
The actual observed value, and now we're going to subtract the predicted value we just calculated, shoe underscore pred. So the difference, that's subtracting the actual observed value, shoe, and the predicted value, shoe pred, that's based on those regression numbers.
Okay.
Okay. That's for the shoe based on age. Now we're going to do reading level based on age. So read pred. So you just need to change those, the numbers, and we wrote those down. It was negative 2 point. Make sure you get the negative.
Yeah. Oh, sorry. Yeah. Negative there. 2.748.
Perfect.
And then
The-
0.7631.
Yep, 7631. So you're going to do actual reading level they were minus what we just found out the prediction would be. Great. Now, if you run it, you're going to get an error because check out the very last thing on the last line.
Oh, yeah, it's piped.
Pipe going nowhere. Yep. Okay. And now your next chunk, you can take off that hashtag at the beginning,
Mm-hmm.
and it should print out your child new data set. No, on the next chunk.
Oh, on the next one. Oh, okay. Perfect. Thank you. That was last night at 11 p.m. I'm going, oh man, I don't know what to do.
Yes. We went over this one on office hours yesterday because you are, Brian, not the only one. Everyone had this question. This is one we always do in class. Okay, so let's look at this data set. So we have 8 children, and for each of the 8 children, we actually measured their shoe size, reading level, and age. And then we regressed shoe size on age to get a prediction and a residual because the prediction's not perfect. And then we regressed reading on age and we got a prediction, and then there's a residual because it's not perfect either. Okay. So the next thing you do, and I want to do this together because I want to talk about this really quick if we can. If Brian, you'll be our guinea pig still, if you'll go to the next
Sure.
chart. We're going to do a correlation. So first we're going to do a Pearson's correlation between the original shoe size and reading level variables. So I think the data set, you can call it is, we can call it child new because that has all the variables in it. So let's use child new and pipe it into a core.test. And remember, in core.test, our formula puts the variable names together after the tilde. So we'll put a tilde wave and then the 2 variables, shoe and read. and put the plus sign between them.
Okay.
Comma, data equals dot. Yeah, because the data set's the second thing in the parentheses, not the first. And this will tell us, if you run that, if shoe size and reading level are correlated. Are they correlated?
Yes.
Strongly correlated, right? There is, because the R value, the correlation is 0.87, and the p-value is 0.004. So there is a strong association between shoe size and reading level. Strong association. Is it causal, though? Does shoe size cause higher reading level? A bigger shoe size cause higher reading level?
No.
No. Why? What's the third hidden factor we don't see here? Our confounding factor.
Age.
Age. Age is a confounding factor. Age is driving our observed relationship. We are observing shoe size and reading level as being associated, but it's not because they cause each other. It's because this third variable, age, causes both of them simultaneously to increase. So we want to, if we want to know, so if you see things that are associated and you're like, is it just age, or is there something, are they still connected after accounting for age? We can do what's called a partial correlation, which is basically what we're going to get on the next chunk when we do the same thing. So you can copy the chunk we just finished and paste it into this one. But instead of using the shoe size and the reading level original variables, use the residual versions. And remember, these residuals are coming from a model where that variable was predicted based on age. Both of them are residuals based on age. Let's go back up to our data set and make sure.
Yeah, maybe
Yeah, go up one more line. Yeah.
Oh, I did pred right there. Let's change that.
Yeah, that's fine. Copy and paste is my favorite thing, and it's my most hated thing for that reason. Okay, so now if you look at the correlation between the shoe resid and read resid, what's the correlation R number?
It's pretty low. It's 0.23.
And look at the p-value.
Yeah, it's very high.
It's not significant.
Yeah.
So after accounting for age, there is no longer an association between shoe size and reading level. So the entirety of the connection between shoe size and reading level, it was all being driven by the confounder factor of age. After pulling out the effect of age, there is no longer a connection between shoe size and reading level. And that's the idea of a partial correlation. After parceling out age, what's left? Our answer here, nothing.
Great. Well, that actually answered a number of my questions with that whole thing, so we're good. That's good.
Yeah. You know, this I think something we've all learned from this online learning experience we've all been having for all age of students recently is that having a conversation is important.
Yep. Great. That's it for me on that one. Thanks.
Anyone else have any questions about Chapter 10 homework?
Can I ask a question?
Absolutely.
Okay, this is more towards the end. I don't know if you want me to share my screen. I can't.
That would be fabulous.
Okay, 1 second.
These are great questions.
Okay.
So this is section C.
Yes.
C.
So I've gone through and done the linear model.
So this is where you're supposed to do it separately. Oh, so this first one here, anxiety and phobia for the full sample. Wait, is
Right.
Yep. So you do not need the filter statement to do the full sample.
Okay, so I don't need to even put in the dplyr.
No, you don't need a filter statement to do the full sample. It will do that automatically. I would suggest that you pipe on the word summary at the end so you get the more complete output.
Okay.
That can be really helpful.
Okay. So I think that one ran okay, even though I had the extra phrase in there.
Yep.
But the next one, I'm not
Yes.
working.
Okay. You are so close. Did anyone get this one to run where you're supposed to filter out and just run it on just men and then just women?
Kimberly's nodding, sort of.
Kimberly's
I
not.
think I did. Pretty sure I did.
Can you see anything in this
Oh
code?
yeah, she needs quotes around male.
Any quotes around the word male?
Okay. Oh, yep, that's in there.
Because it's just text. And again, if you pipe on the word summary at the end, you'll get the more complete output.
Okay.
Yeah.
Oops. Oh. Okay. And then the same thing with this one.
Quotes around the word female. Yep.
Yeah. Okay. That was my last question for 10, so thank you. Okay, thanks.
I think that's most of we didn't do the very first one, but that's good. Okay, any other questions? Okay, let's take a 10-minute break. Go get something to drink, walk around. We'll come back, we'll do calendaring, and then we'll cover the paired t-tests. I'm gonna look at the calendar while we're having our break. Oh, Canvas, Canvas, Canvas. It's not letting me save a changed due date on the quiz, on the exam. Why, oh, why? Okay, I'm gonna have to, okay. Okay, shall we, are we back? Melissa, Hillary, Kimberly, we back? Hillary's back, yay, Kimberly, Melissa, yay, we're all back. Okay, I'm fighting with Canvas again. So I cannot, it won't let me change the exam due date, but I will force it to change. This is what I've come up as far as the calendar. Let's, and I want your feedback on this. Chapters 9, 10, and 11 homework, knowing that 10 is not online yet. And the exam, have them do Sunday night. Is that adequate? And then, I didn't change this one too. I was gonna make the chapter 12 discussion not due till Tuesday. What? Yeah, because that'll give you Monday to read it and then do the discussion by Tuesday. And then we'll be back online. Does that work? Okay, better. That's better than we had it, right? More realistic.
What's the exam?
The exam I'll have to change to Sunday, May 31st at midnight. It won't let me change it for, like, I come in here and, am I sharing my screen? I'm not sharing my screen. No wonder you guys are great. Let's see, share screen.
Okay, so if the exam is due on Sunday, when will that open up?
As soon as I get homework 10, tonight, I'll have it done tonight. I'll have it done by tomorrow morning. I'll tell you that. It'll be open by tomorrow morning, and then you'll have till Sunday midnight to take it. How's that sound?
Okay.
Because I want you to have several days, at least 2 days to take it. So if I finish it by tomorrow morning, you'll have tomorrow's Thursday, Friday, Saturday, Sunday. That's 4 days. Although you probably won't. I don't want you to have to take it on a Sunday or a Saturday, if at all possible. But if you need it, it's there.
Okay.
Because life. Okay, so I come into Canvas. I go to edit the, it let me do the assignments. Come down here, and I tried to change it due on the 31st and opening tomorrow morning. And I push save and it won't do anything. And if I go anywhere else, it doesn't.
There's a little checkbox at the very end that says notify users of change. Does that make a difference?
I don't think so, because I don't usually do that. It has a, take off that. I've never had it do this before, and I've changed all of our test due dates this semester. So I don't know what's going on, so I'll have to fight with that later.
Is it because it's still, because you have 0 points up there?
It has 0 points. What in the heck?
Feed up there by public?
I actually saw that earlier. The value is 0 points.
I don't know if that's the reason why, but
Where does it say 0 points?
By published.
Okay, that's because I think it has 0 questions in it right now.
Oh, okay. Gotcha.
Let me add a question. True. Correct answer. True. Big question. There. There it has a question in it. But it you can create quizzes without empty quizzes. I don't know. It's 1 point now. 20 minutes. Let's see. Save. But then if I go somewhere else and come back into it, it's back to. It's fine.
Had this happened last semester, Sarah, and
Yeah.
it was because I had a student accidentally like get into it. And I'm wondering if I mean, does any of us have, because like it won't let you change the dates if you've got somebody who started the exam.
Oh, that's true.
It should
I mean-
be like extended out. I know it won't let me like make it earlier, but you think it would let me.
No,
I
it would because of
it.
Proctorio. Like Canvas would, but Proctorio won't.
I might have to delete it and create a new one. Since
Right.
I'm-
That's what I had to do. I had to delete it and then completely make a new one, and Proctorio was fine.
Yeah, I think that's what I'm going to have to do. So so if you see like a new exam pop up, that's what is happening. So don't be concerned. It's just me trying to make Canvas play our game. So yeah, so I will get that fixed tonight. Okay. Okay. That will fix that. Okay. Now, why is it not letting all of our pictures be? There we go. Anyway, there we go. I don't want it over there. Okay. There, okay. I have everyone's pictures matched t-tests. Okay. This will be painless, well, relatively painless. This will be very brief. And I noticed when I was looking at these slides currently do not have any syntax in them. So my plan is to go over these slides and then let's open the homework and we'll use that as our learning how to do the syntax. Because it's really, the only thing new that we really have to do is add paired equals true, this option in the t-dot test. That's like all the syntax new stuff, pretty much. So that's the good news, yay! Chapter 11 is usually fairly painless. So the difference with the t-test that we're talking about in chapter 11 is that we have lack of independence. We have some connection between our two groups or our two groups of scores or measurements. So the most common time that I see this used is like a pre-test, post-test score situation. Can be used in a lot of other situations as long as there's lack of independence. So here's an example. Dr. Fishburne wishes to assess the effectiveness of a leadership workshop or put in whatever it is that you're studying, a teaching unit on this, a therapy session on that, whatever it is. So wants to know about the effectiveness. Here we have 60 middle managers. So the 60 managers are rated by their supervisors on their leadership rating form. That's the measurement tool. So they get a score and they do this before they take the workshop and then it's done again after the workshop. So we have before and after, pre and post test scores. So 2 scores on each person. But these 2 sets of scores are not 2 different groups of people. There's a pairing of a before and an after score together. And that's the difference with this situation versus the other t-tests we've done before. Another type of situation is like this. Dr. Clark is interested in determining if workers are more concerned with job security or pay. I don't know, which one are you more concerned with? Depends on the day. He gains the cooperation of 30 individuals who work in different settings and asks each employee to rate his or her concern about salary level and job security, both of those on a 10-point scale. So here we have 2 items, 2 ratings of 2 different things, but the key here is they are both ratings on the same type of scale. They're both 1 to 10 scores, but one is they're concerned about salary level, another is they're concerned about something different, job security. So in the first example, it's the exact same rating form at 2 different time points, a before and an after for each person. The second situation, we have 2 ratings for each person, but the ratings are about different things taken at the same time, but we still have 2 scores for each person. So both of these situations are a paired t-test or pairs of observations. Here's a third example. Dr. Gale questions whether husbands or wives with infertility problems feel equally anxious. She recruits 24 infertile couples and administers the infertility anxiety measurement to both husbands and wives. Now in this situation, we only have 1 score per person, but the persons are in marriages or couples. It doesn't say marriages, well, it says husbands and wives, but we have couples. So we have husband score and wife score as a partnership, as a pairing. So all three of these situations, the key here is we have a pairing of our observations. Remember with our t-test, the number one assumption was that we had two independent samples. Here we are violating that assumption of independence, and it's not a bad thing. Lack of independence can be a good thing if you leverage it. The worst thing you can do is ignore the connection between these observations. The best thing you can do is make sure you use a model or a modeling technique, a statistical technique that matches the data that was gathered, the situation that's being studied. Here we are purposefully studying things that are paired. Before is paired with after, husband's paired with wife, salary level rating and job security rating. They're all partnered up. We've got pairings. We want to leverage that. So in the independent groups t-test that we learned about before, we had the assumption of two simple random samples where each sample is representative of its population. And all the members in each sample were independent of each other. There was no connection between the two samples. Whereas here, we have dependency. Every score in this pool or lump is paired with one over here. There's one-to-one pairing. Now, I'm calling this a matched pairs t-test, but this mathematical model, it goes by a ton of different names. It's sometimes called a matched samples t-test, a matched pairs test, a paired samples, related samples, correlated samples, dependent samples, non-independent samples, repeated measures t-test. All of these labels are somehow conveying the idea that we have pairing of scores, pairing of observations. So we could have parent-child dyads, litter mates, twin studies, again, a lot of times pre and post-test scores, or two different measurements on the same person or on the same couple. They're all situations where we have this connection between our observations. In an experimental setting, this might be because we matched groups, and we can match people based on their sex, age, education, on and on and on, different dependent variables. And there is a really big bonus to matching. The big bonus about doing a matched groups study is that it reduces potential confounding factors, so that we know that our independent and dependent variable relationship is not influenced by possible confounding. So we just finished, when Brian shared his score, about the shoe size and the reading level. We saw an association, but it was confounded or driven by the third factor, age. We want to control for these possible confounding factors so that we can really know if there's a causal relationship, or instead of being driven by a third factor. Those third factors, those confounding factors, are the things we would want to match or control for. And this is a really huge benefit of matching, is that you can say, net of the effects of sex, age, and education, these things have a relationship, or this relationship exists, or this difference exists. The problem with this is knowing what to match on. So matching has the benefit of being able to say net of these confounding factors, or control for confounding factors, but you have to know what the confounding factors are, and you have to be able to measure them accurately. So in the example we did with the shoe size and reading level, it's kind of obvious shoe size and reading level don't have any biological reason why those would be connected. And most of you, if I said shoe size is related, causes larger shoe size cause higher reading levels, you guys would be like, no. And it's pretty transparent that age is the driving factor. But not everything we study is that transparent. And so this is the reason why in observational studies, we cannot jump from association to causation, that there's that gap that we have to be cautious about. In an observational setting, a lot of times we can't do matching. We just have the groups that we have. So instead of purposefully matching participants, we still want to simultaneously or successively in a row take repeated measurements. When we do repeated observations, we can let each person be their own control group. when we do and that's why pre-test and post-test are so great, is the pre-test score is the control group for the post-test score on that person. So in a repeated measurements or repeated observation or successive design, you have two observations separated in time most often. You have a pre-test and a post-test, time 1, time 2. They are often called a longitudinal design in that setting. All of those phrases mean the same thing: repeated measure, successive design, longitudinal. When we have this going on, these repeated observations, there are some things that we can complicate the design or the data collection, some things that can go wrong that we need to be aware of. One of those issues is crossover, the crossover effect. So a classic example is like if we were studying diabetics. Diabetics have trouble if they need insulin. Say we had two different medications that we could give them, A and B. Now we could split our group in half and give half only A and half only B. But what if some people, one is better than the other? There's some confounding factors. It's more powerful if we are able to give everyone A and then everyone B. So everyone gets both of the treatments. Now, this is not feasible in all situations, but it would be better if everyone got to try both A and B. So they both get to be in the control group and the treatment group, or the A group and the B group. But if we give everyone A first and everyone B second, we can have some problems. What if drug A does a really, really good job, and then we give everyone B later? If the drug A has done a really good job, then that effect might carry over or cross over after we switch medications, because their diabetes is well controlled. They're starting out at a really good spot when they get drug B. So we can have carryover or carryover effects. So crossover design and counterbalancing, it's nice to be able to give half of people A first, followed by B, and the other half the reverse ordering. So that's the idea of counterbalancing, where we have half the people get one order and half the people get the other ordering, even though everyone's getting both. Now, in a pre-test, post-test, this is irrelevant because you want to know before and after. But if you have a situation where you can have everyone be both in the treatment and control group, or have both treatment A and treatment B, it's better if you're able to do half one ordering and half in the reverse ordering to counterbalance in case you have carryover effect. Now, carryover effect is not eliminated just by having half have one order and half have the reverse order. Often we need to have an extra issue where we need to have what's called a washout period between the two. So in the diabetic situation, example, if we're giving people drug A, say we're monitoring them for a month, and then we switch drugs and give them B, and we're monitoring them for 2 months, what do we want to start measuring the day we change? No, we want to leave some time for the effects of the first situation to wear off and the effect of the second one to come into full effect. That's the idea of a washout period. Now, all of these things, crossover design, counterbalancing, carryover effect, washout period, all of these things are not statistical methodology. They're more study design issues that need to be figured out before in the proposal stages, because they have implications on what data you end up collecting and what it might mean down the road. So, I mean, it's very obvious with the COVID situation right now. Modeling projections, garbage into a model, garbage out. And so we want to be very, very purposeful in our planning stages to try to cut these problems off ahead of time, because if you don't think about these things and you just go gather data and then you come to your statistician later and say, I have a problem, the statistician's going to say, can't fix it. And so this is why your proposal is always vetted either with your committee or a grant board or co-authors, and you want to get input on study design in every stage, especially the planning stages. Now, there's always things that crop up, but the idea here is if we can, and we're not doing a longitudinal necessarily for the effective time, but we have two conditions or two scenarios that can both be offered to each person. We want to have both orderings available and maybe having a washout period between the two. Do you guys have any questions or thoughts about this? What do you think when you read about this? Have you guys seen studies that have these things involved in them?
This is still so new to me. Sorry. Oh, I was just saying this is still so new to me. I'm still absorbing.
Yeah. Kelly, did you have a comment?
Well, I remember I was on a hiring committee and we were talking, like when you go through the people, their research that they'd gone on, like you would hear a lot of this kind of stuff when somebody would ask them a lot about it. So like, what did you do? And so that's what's coming back. That's very reminiscent of me. Like, oh, makes sense. A lot of sense now.
Yeah.
Yeah, like for my dissertation, I know I'm going to have to do something like this because I am giving a pre and post test for attitudes towards statistics.
Mm-hmm.
So my students are going to get a pre and a post. They're going to be matched in some way. So not quite sure what else I'm going to do, but
with pre and post design, you can't do both ordering. You can't have post coming before pre. So you can't counterbalance with pre. And that's okay because the purpose is to see the change from pre to post. But if we're doing two things that are not pre and post, you want to see if you can give both orderings. So, yeah. Okay, that is the only slide. That's all the slides I have for you. Well, that was pretty quick, wasn't it? Should we see the homework? Okay, let's see. I think that's, instead of me coming up with some new things, I think that would be a really good use of our time to go over the homework. I think there's quite a few chapter 11. Yeah, there's quite a few chapter 11 homework problems. Okay.
Are we looking at the Canvas or at the R?
Let's do the R. Let's do the R specifically. Okay.
can we do the G power 1, 2?
Oh, yeah. Should we do the G power first? Let's do
I would
G
not complain.
Okay. So I think I'm still sharing my screen, right? Okay. I'm gonna get my G power. Where's my G power button? There it is. It's on my other screen. Okay. Okay. Can everyone see my teeny tiny G power? Okay. So, matched pairs design. So the G power problem, Kimberly, is which number?
It's item 6, so that is 11B. Oh, yeah, 11B, 11, and 13.
Okay. All righty. Okay. Let's see, go into home. Let's go to student view, assignments, homework 11. Start. Yes. Start. Okay, I do want to point out this. This is the first item. So we've got these formulas. So this top box is the green. This is formula 7.8 from back in chapter 7 when we did independent groups t-test. This blue box down here is formula 11.2. This is the paired sample t-test. And I want us to look at them and see what the difference is. So on this top one, the green one, both of these are t-scores. What's on the top of the t-score? It's a fraction. On the top is the difference subtracting the two group averages, x bar 1 minus x bar 2. That top part of the fraction, that's the same whether we're doing an independence groups t-test or a paired samples t-test, or matched pairs. Matched paired, paired, repeated measures, whatever. It's the same top part to the fraction. I want you to look at the bottom of the fraction, the standard error part. In both of them, it's a square root. In this top one, this is for the separate, this is when you have same size groups and you're doing the separate variances. So we've got variance, because it's S1 squared, the variance of the first group plus the variance of the second group. So it's the combined variance. If you look down here in the blue box, we have that exact thing. But what do we additionally have? We have this new piece. And this new piece is a subtraction. We're subtracting, and what is in that new part we're subtracting underneath the square root in the bottom of the fraction? We're subtracting 2 times rho times S1 times S2 divided by n. What's that rho?
That's got to be your correlation coefficient, right?
It's
Your
the correlation coefficient. Rho is for when it's the whole population, but we can substitute it with R if we only know the sample. That's the correlation between the two measurements. If we have independent groups, what's the correlation? Independent groups means there's no correlation. The correlation would be 0. What would happen if we plugged in 0 for rho down here in this blue box? We'd get 2 times 0 times some other stuff divided by n. We got times by 0 in there. What would happen to this chunk, this 2 rho S1, S2 over n? What would happen to that when we plug in 0 for the correlation? It basically, poof, turns into 0 and it vanishes. So this green box, the separate variance test, and the blue box, the paired samples t-test, are identical if the correlation is 0. So the green box is based on the assumption of independence, correlation of 0. It's like a simplification of the blue box. The paired sample allows you to leverage or include the correlation that exists. The other thing I wanted to point out is the degrees of freedom. Look at the degrees of freedom in the green box. Degrees of freedom are combined sample size minus 2. Now, if we have paired samples, matched pairs, that means pre-test, post-test, husbands, wives, parents, child, everyone's paired. So what do we know about our group sample sizes? The size, how many pre-tests do we have compared to how many post-tests? They all have to be paired, so it's the same.
Yeah.
So N1 and N2 are the same number. We have to have complete data to include it. Every pre-test has to have a post-test. If you only have one, you can't use it. It's not paired. If you have a husband without a wife, you can't use them as a dyad because you don't have both. So N1 and N2 are the same as N. We get N minus 1. N is the number of paired observations minus 1. Okay, so
Basically half of what you would have up in the top one, because when you pair them, you only have half the samples.
So the degrees of freedom are half, okay? So there are pros and cons to everything. A paired sample t-test, the pro is you can leverage the strength of the correlation. That means we're going to subtract whatever we put in for rho. What rho is correlation? What numbers, what are some of the kind of number we get for correlation? It's going to be
Between
like
0 and 1.
Between 0 and 1. It's going to be a decimal number, exactly, like 0.7, 0.2. It's going to be a decimal number. So we're going to get, let's see, got a decimal in the top times 2, as the correlation, we're subtracting something from the bottom of a fraction. So if we subtract something on the bottom of the bottom of the fraction is going to get smaller. What happens when the bottom of the fraction gets smaller? Instead of dividing by 4, we divide by 3 or 2. We're dividing by a smaller number. So the t-score is bigger. So what happens when you do this blue formula is you get a bigger t-score compared to the green box. When you do a paired samples t-test, you leverage the correlation to get a bigger t-score. That's the pro. The con is you only have half the degrees of freedom. That's the con, is your degrees of freedom for the paired sample t-test are half what it would have been for the independent groups t-test. So doing the matched pair, the pro is we get a bigger t-score, the con is we get less degrees of freedom, half the degrees of freedom. In the real world, the pro is a lot better than the con as long as there is correlation. So if there is correlation, leveraging it is well worth cutting the degrees of freedom in half. And so it makes the paired sample t-test more powerful in the presence of correlation. If there was no correlation, we would get this bottom of the fraction would be the same because rho is 0. And so we would only get the hit on degrees of freedom. We'd only get the con, no pro there. Okay, I wanted to bring that up while we were there. Which I guess brings me back to our formula sheet. So formula sheet. So remember we did our one sample Z and T test at the top, and then we did our paired sample or our independent groups T test at the bottom. Now we're doing the matched pairs. That's this gray bit in the middle of this formula sheet. Matched pairs. Matched pairs is somewhere in between a one sample and a two sample because of the correlation. And on the side here, under where it says matched pairs, it says n equals the number of pairs. Usually n is the sample size. Here we're saying number of pairs of scores. We still want to know what's the difference. D is the difference. D bar. Now there's two ways to do a matched pairs t-test to do the math. One is called the direct difference method. The other is called the correlation method. So the formulas we just saw on the green and the blue box on the, item 1 of the homework, that's the correlation method, where you do the T formula, where you put R or rho, the correlation, into the bottom of the fraction. That's the correlation method. To do this method, let's see, to create this t-score, what do we need? Well, we need to do the D bar. D bar is the difference in the two averages. We need the two averages, the pre-test, post-test averages, or the husband-wife averages. Then down in the bottom of the fraction, we need the two variances, which is standard deviation squared. We need n, the number of pairs, and we need R, the correlation. You can create this t-score by having the two means, the two standard deviations, the correlation, and the number of pairs. That's the correlation method. That works good if you have summarized data. So the ones that the book has you do by hand, use this correlation method. The direct difference method, instead of subtracting the group averages, for each pair you subtract them. So sometimes this is called gain scores or difference scores. Have you guys heard of a gain score? Is that not in the language? It's used a lot in education for pre-test, post-test situation. We want to know how much somebody gains. So that's the gain score. We take the post score and we subtract the pre-score. We subtract them to find out how different they are. And usually things are going up, so it's a gain score. Sometimes we call it, if it's not a gain, like if we want to decrease a depression score, we call it a loss score, or a difference score. It's how different the two scores are. So notice that in this bottom gray box, it has D with the bar on top. That's when we subtract the averages. This top gray line has D without a bar, and that's for each pair we subtract the 2 scores, for each pair. Not instead of doing it on the averages, we do it on each pair. So we go from having 2 scores, a pre-test and a post-test for each person, to only having 1 number for each person, the difference between the 2. Then it becomes basically a 1 sample test. If you subtract your pairs, you go from having 2 scores for each observation to having 1 score, just the difference. And we can do the standard error and the t-score just like we did a 1 sample test. So if you look at this top gray line, it's hard for me to highlight it here, you'll notice that that looks a lot like the line right above it. Do you see that? The standard error is standard error for the differences over the square root of n. And the t-score looks a lot like the one right above it. It's the average difference minus the hypothesized mean difference over standard deviation divided by the square root of n. So the homework has you do 1 problem. Let's see, which one is it? Both ways to show you get the same thing. I think it's the third item. It's, yeah, 11B number 3. If we have time, we'll go back and do that one, but I just wanted to show you that. Okay. So going back to, oh, we want to look at that before we go to G-Power. We want to look at the homework. So item number 6. So item number 6 has you use G-Power. Okay. So there's some information here. It says rounding rules for numbers coming from G-Power output. We're going to use 2 decimal places for all number except for whole numbers for sample size. Sample size better be a whole number. Okay, imagine that an experiment is being planned in which there are 2 groups, each containing 25 participants. So we can have matched D-scores and unmatched D. D is Cohen's D, the effect size D, the difference. This is a little d, not the capital D that was on the formula sheet. Capitalization means it's different. Okay, so unmatched effect size D is about 0.4. Now there's this formula 11.5. This is, now that you've got 2 different little d's in this formula. We've got a plain little d on the right side and a d with matched. It says D matched. That's the Cohen's D for a matched one on the left side. This is a formula you can use to convert an unmatched Cohen's D to a matched Cohen's D. So we are given some information here. We have 2 groups, that's great. 25 participants, so that's our sample size. 0.4 is our Cohen's D, so that's this plain D. Now in part A, it says if the groups are to be matched and the correlation is expected to be 0.5. 0.5, it's what number in this blue box? Which letter does it go? Where does it get plugged in? The 0.5. That's the row. 0.5 is the correlation. Correlation is row. Okay, so let's do this formula in this box first. So we know Cohen's D out in front of the square root is 0.4. Then under the square root, we've got 1 divided by 2 times parentheses 1 minus row, and row is 0.5. So let's do the parentheses first, inside out. 1 minus 0.5 is 0.5, okay? Then 2 times 0.5 is 1. Good. These are nice math problems. I like these. And 1 divided by 1 is 1. Okay, we're doing good. I can do this in my head. And then the square root of 1 is 1. So we get D is equal to D matched. What are we plugging in for D? 0.4. So our D matched will also be 0.4. If the correlation is 0.5, the unmatched Cohen's D and the matched Cohen's D end up being identical. Okay, so our correlation is 0.5, Our D-matched is 0.4 as well as our unmatched. And the power, we want to solve for power. That's what we're going to type in this box. Alpha 0.5 two-tailed test. Okay, two tails, alpha 0.5, solve for power. Let's go to our Cohen's D, or our G power now. Okay, we got to get our drop-down menus right first. The first one's a t-test. We're doing a t-test. And we're doing t-test for correlation. Nope, that was the default. We're doing our t-test, or what kind of t-test? Before we've done two independent groups. Now we're doing two dependent groups, the matched pairs. Okay, so those are the first two drop downs. Now the third drop down, what are we trying to solve for? We're not trying to solve for sample size here. We're trying to solve for power. So that's the post hoc. Okay, now let's get our inputs right so we can get our outputted power. How many tails? 2. Effect size DZ, 0.4. Alpha, 0.05. Now it says total sample size. Ah, did we have total sample size? 25.
Is that 25 or 50? Because there's two groups.
Yes, this is total sample size. I believe it's 25. Let's plug in 25 and see if we get the right answer. I believe it is. Let me see. Yes. Yeah. So the total sample size here is total number of pairs. So it's 25. So we have 25 in each group, but we have 25 pairs. So it's sample size of 25. So what do we get for power? .484. Now, everyone hold tight on the putting your answers in, unless it says how many decimal places, because I'll add the plus or minus margin of error numbers tonight, okay, after I write your test. You get that live. So on this one, the answer should, if we're going to go 2 decimal places, the answer would be 0.48, which I think is what it's marking correct right now.
And with power, we don't put the 0 in front.
Nope, power, because it's always going to be point something. We don't need to put the 0 in front of it. You're right. 0.48. So that's part A. So we'd say, I will check 0.48. Let me check my answer. Oh, there's a second box. That is right, 0.48. Okay. Now this part B says, what if the correlation in the exam, what if it was 0.7 instead of 0.5? Now this is something in G power, this DZ, this is supposed to be the matched Cohen's D. The unmatched Cohen's D and the matched Cohen's D are only the same thing if the correlation is 0.5. Now there is this little determine button. You guys see the little determine button? I like this. Let's see if you can hear it. Let's see. I'm gonna turn up my volume. Oh, you didn't hear it. Did you hear it? I didn't hear it. It usually goes whoosh when it pulls that out. It's kind of fun. Okay, so if you know the means and the standard deviations, so a Cohen's D means the means are different. The interpretation of a Cohen's D of 0.4 means the means are different by 0.4 standard deviations. Okay, so if the groups go from 0 to 0.4 with a standard deviation of 1, that's a Cohen's D of 0.4, and the correlation 0.5 means that the Cohen's D of 0.4 unmatched translates to Cohen's D matched 0.4, so they're the same. But if the correlation was we're supposed to change it to what, 0.7? this is the, so if we go back to this formula in the blue box and we put in row of 0.7, I have to use our calculators perhaps here. 1 minus 0.7 is 0.3. 2 times 0.3 is 0.6. 1 divided by 0.6, before I get out my calculator. 1 divided by 0.6 is 1.666667. Now we have to do the square root of that. So I turn my cell phone to the side to get the scientific calculator to get my square root button. Is 1.29, and then times that by 0.4. What do you get? Notice what I got over here in my window. So if you didn't know that DZ was the matched Cohen's D and you put in the plain Cohen's D, then G-Power treats it as if the correlation is 0.5. And people don't know that. They use Cohen's D and they put a regular Cohen's D in here, and they don't know that it's assuming that your correlation is 0.5. That Z next to the D means this is the matched Cohen's D, not the regular unmatched Cohen's D. And that blue box formula 11.5 is the conversion if you want to do it that way. If not, you can use this little calculate, determine, calculate, push out. But this is something that's very misunderstood about the matched power in G-Power. I find people always misusing it. They're putting a regular Cohen's D in here instead of matched Cohen's D. So we're going to put what? Well, you can put this calculate and transfer in. That's one way to do it. So it's the matched Cohen's D is 0.5164-ish. And now when we push calculate, the power is now how would we round that? 0.70? Yes. Okay, so what happens here? If the correlation is higher, what happens to the power? It goes up. If you have more correlation, it makes a more powerful test for detecting the difference. There's more that used Cohen's D, right? Yeah, so this top one is asking you to calculate power. This bottom one is asking you to calculate sample size. Okay. So let's see. A matched t-test is being planned to evaluate a new method for learning foreign language. The only language I know is mathematics and statistics. Took French for a semester in high school from the baseball coach, and it was spring. Guess what we learned? Baseball. Okay, so from previous research, like publications from a lit review or other stuff, the unmatched effect size is 0.3 and the correlation is 0.6. So to use G-Power, we have to use this formula to convert from a regular Cohen's D to the matched Cohen's Z, which in G-Power is the DZ. I think you guys can do this one now, don't you think so? Okay, fabulous. Okay. Okay, let's see. Let's go to, let's see, 11B, is that item number? Which item number is this? Oh, yeah, this is the one that has you do it as two different ways. As the direct difference and as a matched t-test. let's see, we've got 20 minutes. Yeah, let's do this one. We'll do this one and then we'll do one of the section C one. Office hours will be tomorrow at 7. It's my last time in the car doing office hours. I haven't been able to record office hours in the car because I'm on my cell phone, but starting Monday, the high school swim team, the swim teams can use the high school swimming pool, so I don't have to go to Logan, so I can stay home. Yay. Okay, so here we go. Here.
So we actually only have 5 minutes left.
Oh, because we go to a quarter after. I always think we go till 4:30. Oh, I'll let you guys choose. Do we want to do this one or do we want to do section C? What do you guys want? This one? Okay, this one we do it in R, so that we'll get R in here. Okay, so this is some data. We have GRE scores. We have people that took the GRE twice. Did you guys take the GRE twice or just once? I only took it once. Who wants to take it twice? Not me. Okay, so specifically we have their verbal scores. So we have the first time when they took it and the second time they took it. So we want to know, is there a difference? I think they had a training between the first and the second time, and we want to know, did it change their scores? Was there a difference between the first time and the second time? So let's go into R up here. Okay. Okay, let's open R. Now, I've already entered the data into R for you. I already typed it in, so that's yay. Don't have to do that. Where's my R? Where is it? Oh, it's back here. Yeah. Okay. Oh. Okay. Okay. Load our packages. Okay, so here are all the toy data sets we need to do the homework. So here is the GRE data set. So we have 5 subjects and we have their 5 first GRE scores and their 5 second GRE scores. Okay, so here is the way the data set looks. So we've got ID 1, 2, 3, 4, 5, verbal GRE underscore 1 and verbal GRE underscore 2. Okay, so let's do the paired sample first. So we start with the name of the data set, GRE, and now we're going to pipe it into t.test. This is the out-of-date syntax. Oh, yes. Okay, so this is using tidy gather. Tidyr gather is an old command. Do we want to change to the new command? Let's change to the new one. The new one is a lot easier to use. It's tidyr pivot longer. I need to make a video on this. Okay. Pivot longer. Pivot longer. So right now the GRE scores are side by side, right? We need to make it so they're stacked into the same column. The old command was called gather because we're going to gather these two together. It's like if you have a deck of cards, if you guys shuffle the deck of cards with the bridge where you shuffle them so they go together like this. Instead of having 2 piles, you shuffle them together to make 1 pile. That's basically what we want to do. And so that was the gather command, but we're going to use pivot longer. So first thing you have to do is tell it which columns, COLS, we want to shuffle together. And they're called verbal GRE underscore 1 and verbal GRE score number 2. So we need to concatenate or combine those together. So pivot longer, we're going to tell it which columns we are going to pivot and make it basically shuffle them together. And then we have to say, create 2 new columns, names 2. So we're going to call this time. Now, how do we know which time it is on the score? It's this right here after the underscore. So we're going to say names pattern. Both of those names say verbal, GRE underscore, and then after that there's either a 1 or a 2. We want to keep the 1 or a 2 because it tells us which time, but all the stuff that precedes that, the prefix, verbal, GRE underscore, is just not needed to know what time. Then we're going to say values equal, and I'm going to say verbal GRE because it's their verbal GRE score. Or it's names underscore 2. Oh, it's names prefix. Okay. Get that all. Can't quite get that all on my own screen. Okay. Looking below the syntax, looking at what this worked. We went from person number 1 in the original data set. Person number 1 had 1 line and their scores were sitting side by side, right? Now in this data set had 5 rows. When I run this command now, we have 10 rows. Our data set became longer. It became longer because instead of each person having 1 row, now each person has 2 rows. We have their first time point and their second time point. They're stacked together. We've taken the data set from having the variables side by side to having them together. Yes, say it.
So what is, it says names prefix verbal GRE underscore?
Mm-hmm. Because that is what precedes the number 1 and the number 2. We only want 1 and 2 to be kept in our time variable.
Okay. And then the values 2, that's an equals after values 2.
See, if I change this to score, that's what it's going to name this new variable where it puts the numbers that were side by side here.
Okay. Okay.
What do we have? What did I say to do here? Did it say? Didn't say. Oh, it says to say verbal GRE. Okay. This is a preparatory step. To do the paired samples t-test, you have to shuffle these together and pivot it to longer format. Now we can pipe it into the t-dot test. So we only have 1 group of people here. We only have 5 people, but it's like we have 2 groups. There are 5 people with their pre-scores, and we have the same 5 people with their post scores. So we need to write the formula. The formula is going to be the continuous interval ratio score that we're comparing comes before the tilde wave, and then after the tilde wave comes the grouping variable. So what's the continuous interval ratio variable that we're comparing between the pretest and the post-test? We're comparing the
Score.
verbal GRE. So that's going to go before the tilde wave. And after the tilde wave, we need to have the grouping variable. Now, we only have 1 group of people, but we have it repeated pre-test, post-test. We have it repeated on time. So time is our grouping variable. And then we have to say data equals dot, because the data is flowing from above, not to the first spot in the parentheses, but after the formula. Now this is the new part. Besides that pivoting thing, that's new. I forgot. I thought I had the data sets are pre-prepped, but I didn't. Okay, we have to add 1 more thing in this parentheses. We have to say paired equals true. Now, if I left out that paired equals true, it's going to do Welch's sample t-test. Or if I say NA dot, what was it? var dot equals true, it'll do the independent 2 samples t-test. But to do the pre-test, post-test match pairs, I have to say paired equals true. So this part of the instruction, after the data set is gathered, add the t.test function, which needs at least 3 arguments. The formula, which is the continuous interval ratio variable we're comparing, tilde wave grouping variable, which here is a repeated measure, time. Then we have to say data equals dot to pipe it from above, and then we need a specified paired equals true. So the mean difference is, on average, the GRE scores are different by 8. Now it's negative because the order it subtracts in. And then our t-score, what are our degrees of freedom here? 4. Why degrees of freedom 4? Because we had 5 pairs of observations. It's number of pairs minus 1. And then there's our t-score, and let's look at our p-value. Our null hypothesis is nothing going on, no difference. Are the two time 1 and time 2 scores different? Yes, they're different, but is there evidence, statistically significant evidence they're different in the whole population? No evidence of a difference. Well, let's see. Bring this up here. So the t has 4 degrees of freedom. It's equal to negative 0.93. Do I need the 0 in front of this decimal in the t-score? Yes, because a t-score can be bigger than 1. And then my p-value is 0.405. We want to give 3 decimal places to a p-value. Now the other way is to subtract these 2 scores. And I can do that here by taking my original data set and subtracting them. Now, did it say which order to subtract them in? The first minus the second. So let's do verbal GRE underscore 1 minus verbal GRE underscore 2. Okay, that creates our difference. So this first one, 540 minus 570 is negative 30. The next one's negative 10. The next one's negative 20, positive 20. And the last person, what's their difference score?
0.
0. There is no difference. Okay. Now compute the 1 sample t-test on the direct differences. So we're going to, let's call this GRE new. There it is, GRE new. To do a 1 sample t-test, what do we have to do? We have to pull out the variable. Oh, I needed to call this something. Call it GRE, verbal GRE difference. There's our verbal GRE diff. So we want it to do a t-test, one sample t-test. We need to pull out the difference variable, GRE, verbal GRE diff. And then in the t-test, we have to say what our null hypothesized average is. If there's no difference, mu is equal to a difference score of 0. Let me shrink this. What do you notice about the paired samples t-test and the one sample t-test on the difference scores?
The difference between which one? Sorry.
Up here on the top of my screen, I have the paired samples t-test. When I did that shuffling thing, the pivot longer, and then did a paired equals true, 2-sample paired test, versus down here at the bottom of my screen, I subtracted the values and did a 1-sample t-test. What do you know about these methods?
They look the exact same.
They are identical.
Why is that?
Remember our formula sheet?
Yes.
The direct difference method, that's the second one we did, where we subtracted each pair and did basically a 1-sample test. And the top of my screen is this correlation method, basically, where we're doing the match pairs test. They will give you identical answers, always. There are 2 different ways to do the same math.
Okay. So the paired t-test is the same thing as the 1-sample t-test?
On the differences.
On the differences, okay.
We did the variable we did the 1-sample test on was the difference scores. You know what I'm going to do? I am going to, these pivot steps, I'm going to do these for you. What's the best way for me to get you that information? Because I don't want this to trip you up. Would it be better for me to make a video, send it an announcement?
I like the
video.
Video?
I like the announcement because then I can copy and paste it.
True.
I'll type it out and I will make a little video. Okay.
Are you okay if we use tidy though? Or do you want me to go back and change it? Because I did use the tidy function on it.
Well, they're both tidy. You use the gather function.
Yeah, I meant gather. Yeah.
You can use, if you want to use the gather, I'm fine with that. Just know that gather is no longer, it's if you come
Antiquated.
in, it's being phased out.
Ooh, okay.
Oh, I capitalized it. Oh, it's tidier. There we go. So it's, they recommend switching to pivot longer, which is easier, it has more features, and it's being actively developed. They're going to be phasing out the gather. So they had gather and spread that they in the tidyverse originally. So this, trying to shuffle data like this to go from we call it wide to long format, 1 line per person to 1 line per observation, is not trivial, and it's a very important part of wrangling data. And anyone who does repeated observations always runs into this, and it's a hard thing to do smoothly. And so Hadley Wickham and his crew were trying to figure out a smooth way, because the code is clunky in every program I've ever used. no matter what it is. It seems so really hard to learn. And Hadley Wickham says he wants to make coding so that instead of having to climb a mountain of success and claw your way up to the peak of success, he wants to make it so that you fall into a pit of success, that things are easier than not make things harder than they should be. And so his first attempt was with gather and spread about 3-4 years ago. And it was better than some other things, but it just was still hard to remember. The pivot longer and pivot wider was his second attempt, and it does take some getting used to, but it really is a better way to code it. Gather will still work. If you want to use gather and follow the directions that are on this page, go for it. But I will do a video and send out some code if you want to use the pivot longer. It's not like mandatory that you know how to do that. It's a good skill to have, because I can almost guarantee you're all going to need to do it at some point in your real life. But I'll send that out to help you out. We've gone over, I'm sorry, Brian, 15 minutes. You guys have been so awesome to hang in there. Office hours tomorrow, and I will record some stuff for you. And I'll get that test 3 figured out. It will be open in the morning and through Sunday night at midnight. Homeworks 9, 10, 11 will be due Sunday night at midnight as well. Guys, can you believe it? We're going past halfway now.
Hooray.
Okay. The chapters do slow down, because you'll notice we've been doing almost 2 chapters a day, class time. Now it drops down to 1. They're bigger chapters, but the pace will hopefully feel a little better. We've dragged you along for a while.
Thank you so much, Sarah.
Yes, thank you.
See you guys
This
later.
video will probably be up later tonight or tomorrow.
I'm going to process it right now. I won't leave the office till it gets processed. Sometimes it takes it 15 minutes. Sometimes it takes an hour and a half.
Sorry.
I don't know how to predict how long it's going to take.
No, that's fine. I'm just trying to gauge when to do what, and then that makes sense. So thank you very much. I appreciate your help today.
All right. Okay. We'll talk to you guys later.
Bye.
Where's my...